All right, so measuring variability or spread is another term we use this for how spread out a data set is. We kind of want to know, when we're talking about distribution, we want to know about shape, center, and spread. We talked about describing those before. Shape, we've already kind of mentioned describing it. We'll get some more terms for that as we go, but symmetric or skewed. Center, we now have mean and median. We can use to describe those. And so we have a few measures of spread or variability. The easiest one is the range. So it's just the range values, that's max minus min. So if we take a data set, like here we have the soccer goals, take the biggest number minus the smallest number, 10 minus 1, we have a range of 9 goals. That measure is not resistant. Yeah, it's a single number. It's affected very much so by just whatever your largest and smallest numbers are. So probably not our best measure of spread, but or variability. But it's a very easy one to give if you're just looking at a graph and asked to describe shape, center, and spread. It's very easy just to describe the range. So then the next one we'll look at is a big one, and this one might actually be somewhat new to you. This is the standard deviation. So this measures the typical distance of values in the distribution from the mean. And we say typical, it's not quite an average distance. An average distance it's got a different name. It's mean absolute deviation. It's a fine statistic, but it doesn't work with a lot of stuff we'll do. So the standard deviation does one thing different than that, finding that average distance away. The average distance away, we'll see how this formula looks out. So the way you calculate the standard deviation, and this is a sample standard deviation symbol, the population standard deviation is slightly different. You find the mean of the distribution, so you calculate your mean, your x bar, calculate the deviation of each value from the mean. So you take your value minus your mean, you find how far above or below it is, and then you square each of those deviations. That's the big difference between finding an average distance and what we're doing here. And because what we want to do is like the distance, we would want to take an absolute value, but absolute value does not work out very well with some of the relationships we'll get into later that actually rely on calculus. Those of you who have taken calculus, you'll know that absolute value, calculus does not like that corner. It's really kind of a piecewise function, and that corner, some of the features break down. So rather than do that, what we do is we square that distance. That has the same effect of we get that squared deviation, and then at the end we add up all those squared deviations, divide by n minus 1. This little minus 1 actually is we call it a Bessel correction, and we can get into more about why that is. If you had the population, you wouldn't do that, but for sample size, the smaller the sample gets, the bigger this does to inflate that standard deviation, and take the square root of that. So we square and then later take the square root on the outside. It gets us very close to an average distance from the mean, but it's not quite. So here's what it looks like in the formula. So we take each data value minus the mean. So that's and if we did an absolute value here, it would be a distance of each data value from the mean. Instead of doing an absolute value there, we do this squared. And so that squared makes it positive so that all these distances are positive. Otherwise, if we just added up all these differences without doing something, it would cancel out to 0. So we do that for each data value, add those all up, and then we divide by n. It's kind of like an average distance, but we do this n minus 1 with this little minus 1 Bessel correction, and then take the square root, and that's our standard deviation formula. So seeing that applied, and this is what it looks like on your formula sheet. When you will get a formula sheet eventually. A sample standard deviation is that formula on your formula sheet, and it's got that summation notation again to account for all these addition of the repeating it for each data value. So for each data value, subtract the mean, square it, divide by n minus 1, however many data values, n is the number of data values minus 1, and square root. All right, so seeing this applied, 11 high school students were asked how many close friends they have. Here are their responses. So we've got those 11 data values. And if you're calculating a standard deviation, it's very nice to have technology doing this for you, because this gets even much more tedious than a mean, for instance. Because the first thing you have to do is find the mean of that distribution. So they've found the mean. They added up those 11 data values and divided by 11, and they got 3. So it added up to 33, divided by 11, got 3. So that's the mean of the distribution. The next step is subtract each data value. So we need to do basically this 1 minus 3, this 2 minus 3. And so you see that's what they're doing here. They're taking each data value, each of these data values, subtracting 3. And so the first data value is 2 below average. The next one is 1 below, 1 below, 1 below, all the way up to 3 above. All right. If we were going to do a mean absolute deviation, we would just add up those numbers and we would make them all positive. We would take the absolute value. Instead, we're going to square them to do standard deviation. So we square each of those numbers. That'll make them positive. So this 2 becomes 4, or negative 1 becomes positive 1. Make sure you get those in parentheses. 3 becomes 9. And so those are our squared deviations. We sum our squared deviations. And then the next step is divide by n minus 1. So, and take the square root finally. So we do that sum of squared deviation was 18. We plug that in here into our numerator. Divide by n minus 1, we divide by 10. So 18 divided by 10 is 1.8. And then the square root of that gives us 1.34. And that's slightly different from, but close to that typical distance the data values are from the mean. The mean was 3. That's kind of like, you can think of it as, again, a typical distance. Not quite an average distance from the mean, but a typical distance those data values are from the mean, because that square root to some extent cancels out the squaring that we did later. It does still put a little bit more emphasis on those big points that are further away. So that is standard deviation. There's another term we use. It's called variance. It's if we did not take the square root. A lot of times it's nice because like that right before we take the square root, we'll have a nice rational number. And then once we take the square root, it's irrational. This number has been rounded. So a lot of times it's just nice to report the variance. But it is weird because the units are squared because we squared at one point our values, so we end up with squared units. So right here it's 1.34 close friends is the units. If we don't take the square root, it would just been that 18 over 10 or 1.8, and then it's squared close friends, which doesn't make a lot of sense, but it's a nice number, nice round, rational number that we can give for variance. All right, so properties of the standard deviation. Because of the squaring, it's always greater than or equal to 0. 0 would be if all the data values were the same. Larger values of the sample standard deviation indicate greater variation. That's also true for the variance. If the variance is bigger, it's more variation. But standard deviation, the larger those values, the bigger the variation. Standard deviation is not a resistant measure of variability because it's taking every single data value into account. It's actually even got the mean in the formula, which is not resistant. It's very much so affected by outliers and skew. And it measures that variation about the mean. So a lot of times if we're using the mean, this will be the measure of spread that we use. We use the sample standard deviation. The last measure of spread that we want to get to today is the inner quartile range. This one's a little bit simpler, I guess. So if we break the data into quartiles, we call these. The quartiles of a distribution divide the ordered data set into 4 groups having roughly the same number of values. To find our quartiles, arrange the values of the data from smallest to largest and find the median. Well, this is kind of nice. They've already got this in a dot plot. So they're arranged from smallest to largest. So first thing we do is find the median, cut it in half. And so if we have this, because of the number of data values here, we've got 6 on the left half here, 6 on the right half. It splits there, and so our median would be between the 28 and 29, so our median is 28.5. So then what we do to find our quartiles is we go halfway in each half. So if I've split this in half, halfway through the first half, I'll split this into these 3 and those 3, and so it's going to be halfway between those two. Actually would average this 22 and this 23 for that data value, and then here I have these 3 data values. We split this in half, and we get those quartiles, so halfway between 31 and 34. That's what we would do to calculate those. And then to get the inner quartile range, you just do the difference of those. So it's really the middle 50% of the data, kind of. It's kind of like the range of the middle 50% of the data, but because of the way this works out, it ends up being halfway between the between here and the 3rd and the 4th data values where that first quartile would occur. And here it's between like the 9th and I guess this would be the 10th, 10th data value. So if we subtract those, that gives us our inner quartile range. IQR there. So looking at it for, not on a graph, if we took, these are travel times for 20 individuals, 20 New Yorkers. If we first want to deal with this data, we need to arrange it in order. So we get it in order. And then we can find the median. So if we have 20, we divide it into 10 and 10, and we get the median. And so we have, right there's the 10th, and then here's the 11th. And so our median is right between those two. And then out of those first 10, we divide that into 5 and 5. And so we have our 15th individual and our 15th individual, and we'll actually find the average of those two. Well, that's 15. And then the next 5, and then the 5 after that will be our average there, so 42.5. And so then if we find the difference between those, Q3 minus Q2, or sorry, Q1, Q2 is another weird way of saying the median, we end up with a inner quartile range for this of 27.5 minutes. And that gives us kind of like that range of the middle 50% of the data. And it's another way of measuring spread. The bigger those numbers are, the bigger the inner quartile range is, the bigger the spread. So it's similar to the range, but it's more resistant, was one nice thing about it. So if we interpreted that, the middle half of travel times for the New Yorkers in the sample is, the range of the middle half of the travel times for the New Yorkers is 27.5 minutes. All right, so that was the goal of that. One last thing I'll mention, if you have an odd data set, this wasn't mentioned here, if you have an odd number of data values in your data set, your median is a single number, and so it doesn't split nicely, right? You have a single number in the middle. So what you do is you would leave that out. Say you had 25 data values, you would have 12 on the left, 12 on the right, and 1 in the middle. Take the 1 as the median, and then for the Q1, find the median of those first 12 values, find the median of those last 12 values. So you'd split those up 6 and 6. Alternatively, if you had like an odd number in the side, you can just have it be a single number, right? If you had like 18 data values, you would have 9 on the left and 9 on the right. So your median would be between the whatever the 9th and 10th data value. Then your quartile would be in that first 9, it would be the 5th data value. You have 4 on the left of it, 4 on the right of it to find that quartile. So those are a few measures of center, mean and median, and our measures of spread, range, standard deviation, and inner quartile range.